All right, so today we're going to be talking about solutions. So everybody, top of your page, we're going to write solutions. Can anyone tell me what a solution is? Anybody know the solution to pollution? It is dilution. Do y'all know what that means? The solution to pollution is dilution. You just add more water and your problem becomes less. All right, so let's go ahead and get started. So today we're going to be talking about solutions. Can anyone tell me what a solution is before we move on? Nope, not that kind of solution. All right, so it is a mixture of substances. Later on, you're going to know exactly what it is. We'll get to it in a bit. So let's go ahead and keep moving. So first thing we're going to discuss are the unique properties of water. So let's go ahead and write that out. Unique properties of water. So these properties are not unique to water. Water is not the only thing that has these. However, we're just going to discuss all the things that make water unique. So the first and most important, and you're most likely going to be tested on this one, is going to be that water is polar. What does it mean that water is polar? It has opposite what? It has opposite poles, good. That means it's got a positive side and a negative side. Let's discuss how that works. So y'all remember Lewis structures? We have oxygen and then we have two hydrogens. How many dots would the hydrogen get? They would get one. How many would the oxygen get? It would get 6, good. And then what would these electrons do from hydrogen? So they're not going to transfer. What they're actually going to do is just move to the center. So one electron is going to come here. So I got to do some erasing. So what ends up happening is oxygen puts its 2 electrons back here, and then this electron from hydrogen goes here, and then this electron from hydrogen goes here. Now, what are electrons attracted to? So electrons are negatively charged. What are they attracted to? They're attracted to protons. Good. How many protons does an oxygen have? It has 8. How many protons do the hydrogens have? Hydrogens have 1. So where are the electrons going to be closer to? Are they going to be closer to the oxygen or the hydrogen? They're going to be closer to the oxygen. So these electrons are going to be very close to the oxygen and farther away from the hydrogen. Now, because of that, our oxygen is going to have what kind of charge? Now that it's got 10 electrons and it's got 8 protons, what's the charge on the oxygen going to be? It's going to be negative. And the hydrogens, they basically only have 1 proton. So what's the charge on them going to be? They're going to have that positive charge. So that's what creates this pole. What we're going to write is unequal sharing of electrons. So the electrons, they're closer to the oxygen. That's why H2O is going to be polar. Now, this is most likely the question you're going to see on the ACP. I can read y'all the TEK just so y'all know. It says, describe the unique role of water in terms of polarity. There you go. That's polarity. So let's go ahead and keep going. So the next one is going to be hydrogen bonds. So there are 2 things that are required for a hydrogen bond. Can anyone tell me what they are? Hydrogen is 1. What's the other one? I heard something that was kind of correct. So we need hydrogen. What else? In order to have a hydrogen bond, we need 2 things. We need hydrogen and what else? All right, it is covalent, but what is it? All right, so I'll tell you. I think I heard it. So nitrogen, oxygen, or fluorine. So in order to have a hydrogen bond is a polar bond. However, it's stronger than a regular polar bond. So y'all remember dipole-dipole? So hydrogen bonds are much stronger than dipole-dipoles. In order to have a hydrogen bond, you have to have a hydrogen that's bonded to a nitrogen or an oxygen or a fluorine. In the case of H2O, you have hydrogens that are bonded to oxygen, so we have these hydrogen bonds. Now, hydrogen bonds, it says here that they're weak. It says they are individually weak. They're weak if you compare them to ionic bonds or covalent bonds. However, they're really strong if you compare them to polar bonds. So when it comes to dipole-dipole, hydrogen is much stronger than a dipole-dipole bond. And hydrogen bonds by themselves are weak, but if you have trillions upon trillions, like moles on moles of water molecules, you have a bunch of these hydrogen bonds, and it's really difficult to break all of them. We'll discuss that in a little bit when we talk about temperature and evaporation, but it's really hard to break all of these hydrogen bonds. So over here we have another example of a hydrogen bond. So we have NH3, ammonia. And an important thing to know about hydrogen bonds is, do they exist within the molecule? All right, so take a look at my screen real quick. So right here, look at this H2O. Right here, what kind of bond is this between the oxygen and the hydrogen? What kind of bond is this? It's a covalent bond. Good. Now, between two separate water molecules, because hydrogen bonds are intermolecular attractions, they happen outside of the actual molecule. So it's the bond between this hydrogen and this oxygen. That's what makes this hydrogen bond. Okay? That's a thing you want to know about hydrogen bond. So hydrogen bonds are the reason, they're the reason that DNA is three-dimensional. They're also the reason snowflakes have this hexagonal shape. They're also the reason ice gains volume when, so water gains volume when it freezes, which we'll discuss on another slide. Any questions on what hydrogen bonds are? No? All right, well, let's move on. So next one we have is going to be surface tension. So what is surface tension? It's a measure of the force necessary to stretch or break the surface of a liquid. Anybody know what this thing is called? It's not a stick bug. A water what? Not a moccasin. All right, so very often students will call this mosquito. This is a water strider. Why is the water strider not sinking in the water? All right, so it might be heavy enough. So take a look at its legs. Why is it flattening its leg out? All right, it's distributing its weight. So it's got 4 legs, which means it's dividing its mass by 4 onto each leg. Plus it's spreading its leg out so that it can stand on water without sinking in. So it's the distribution. But what is it standing on? It's standing on the hydrogen bonds. So surface tension, what causes surface tension? It's the hydrogen bonds. It's the attractions between separate water molecules that the water strider is unable to break. If you've ever been in a swimming pool and then you did this thing where you slap the water and it hurts, that's you trying to break the surface tension. Anybody know what this thing is? It looks like a Geico. All right, so I got a quick video for you guys.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk.
Okay, so real quick, I got another demo for you guys. So let's move to the back of the... Okay, so for those of y'all who were not here, this is what we were doing. We went to the back of the room, and then we added drops of water to pennies with a goal of getting 30 or more. And what we began to see are these domes. And what's keeping the water together? Hydrogen bonds. Good. So the hydrogen bonds, they're what hold the water together. Now, what do we call that? Water holding other water. We refer to that as cohesion. So go ahead and write down that term. So cohesion is water's attraction to other water molecules.
Good afternoon.
Yes, ma'am.
Yes, student Ariana Rocha to go see Ms.
Okay, so cohesion, that's water's attraction to itself. So next one we have is adhesion. And adhesion, that's when water is attracted to other polar things. So we know water is polar, and water is attracted to other polar things. So in the beginning of the year, I showed you guys these graduated cylinders. So if we put water in a graduated cylinder, and I'm going to zoom in just so y'all can see it up close. If we put water in a graduated cylinder, the water sticks to the sides of the container. Where do we measure? Do we measure the highest point or do we measure the lowest point? We measure the lowest point. What do we call this thing? Anybody remember? It starts with an M. All right, so we call this a meniscus, and we always measure the lowest point in the meniscus. Now, why does the meniscus exist? What's the water doing here? It's attracted to what? It's attracted to what? It's attracted to the sides. So glass is polar. So because glass is polar, the water sticks to the glass. What if we were to put it in a plastic graduated cylinder? Would we get a meniscus? No, because plastic is nonpolar. So if you use a plastic graduated cylinder, you get a line that looks just like that. When you use glass, you get a line that looks just like that. So that's the difference between adhesion and non-adhesion. The next term we have is going to be capillary action. So capillary action, that's the ability of water to flow upward against the force of gravity due to cohesion and adhesion. And so before you write this down, I want to show you all what it looks like. So everybody look at my screen real quick. So over here you can see we have a glass straw sitting inside a cup of yellow water. And it's yellow just so you can see the water move. But if you put this really thin straw in the water, what does the water do? It flows up. Another example of this, has anyone ever seen somebody use the diabetes strips? Y'all know what I'm talking about when they test their blood? So they got to poke themselves, they get a little drop of blood, and they use the machine and it touches the blood. What does the blood do? It flows up the capillary. So anytime you have a really thin space, water will flow up that space. And the way it does that is through adhesion and cohesion. So capillary action, you can see it right here. It doesn't look exactly like this because here the oxygen is holding hands. Usually it would be the oxygen holding a hydrogen. But basically the water molecules are going to stick to the walls of the container while at the same time pulling other water molecules up. All right, so everybody take a look at my tree. Everybody look at my tree. Do y'all see my tree? All right, so how tall is my tree? How tall is it? It's about 3 stories tall, so somewhere around 38 feet tall. How does my tree get water from the ground all the way up to the highest leaf? So what do the roots do? How do they work? Is there a pump down there pushing the water up? How's the water flowing up the tree? What is it? Reverse gravity?
Like when it rains?
All right, so can you feed a tree by putting water on the leaves? No. The water has to go into the floor, and then it has to be sucked up by the roots. So how does the water flow to the top? Capillary action, good. So let's all take a look at this leaf. You've all seen a leaf before. What do we call this thing right here? All right, the stem. Why is the stem getting narrower as we get to the end? So that's capillary action right there. So the water sticks to the walls of the stems, and then it pulls other water molecules up. So capillary action is necessary for all plant life. Have y'all heard of the capillaries that we have? Human capillaries? So we have capillaries too. Water, blood flows through our capillaries. But capillaries are very crucial to life. Any questions on what capillary action is? Another example of capillary action is, say you have a cup of water and you put a sheet of paper in it. What's the water going to do? What's the water going to do? It's going to flow up the paper. So against the force of gravity, it's going to flow through the capillaries in the paper and it's going to go upward. Tissues will do the same thing. If you put a paper towel in water, water is going to flow up against the force of gravity. That's capillary action right there. Any questions on capillary action? All right, my last question is, what causes capillary action? It starts with an H. Hydrogen bonds, good. Let's keep going. So the next one is going to be heat capacity. Go ahead and write that down, heat capacity. So water has a high specific heat and it's got a high heat of vaporization. What does that mean? So let's imagine we have a pot on the stove. So here's a pot on the stove, and then here's another pot on the stove. And we're going to turn on the flames for both of them. And then I'm going to put some water in one. So I'm going to fill this one with water. So after, let's say 30 seconds, which pot is going to be hotter? After 30 seconds, which pot is going to be hotter? Why the one without water? Why the one without water? Y'all are right. So the one without water does get hotter faster. Why? What does the water do? What does the water do if it's there? Conduct isn't the word, but it absorbs the heat. So water will absorb the heat, which means it's taking the heat away from the metal. So if you were to pick up both pots and you were to feel the bottom of the empty pot, it's going to feel really hot compared to the one that's got water in it, because the water is just absorbing heat from the pot. Let me give y'all another example of the same thing. So let's say you were about to go swim in your swimming pool, because we all have swimming pools, right? Now, whatever, we all have swimming pools. All right, so here's our swimming pool, and then here's our grass, because we all got really green grass. And then here is our concrete, because we all got concrete, right? All right, so we step outside our house and we step in the concrete, and this is in the middle of summer. So July, you don't have school tomorrow. You didn't have school yesterday. You walk outside, you step on the black concrete. How does it feel? Really hot, probably around 120 degrees. What about the grass? You step on the grass, how's it going to feel? It's not going to feel as hot. What's it going to feel like? Probably somewhere around 90 degrees. It's still warm, but it's not going to burn your feet the same way the concrete will. What about the water? When you jump in the water, what's the water going to feel like? It's going to feel cold. It's going to feel somewhere around 70 degrees, maybe even a little bit lower, depending on the time of day. So in the morning, before sunrise, the water is really cold. At noon, once the sun absorbs, once the water absorbs a bunch of the heat, it warms up, and then that cycle just repeats over and over again. So water temperature in your pool is going to change. However, it's never going to be as hot as the concrete. Why is that? What's water really good at doing? So water is really good at absorbing heat without changing temperature. So it can absorb an enormous amount of heat without its temperature actually changing. And what we call that is specific heat. We're going to get into thermochemistry in a few weeks. When we get into thermochemistry, we're going to talk about specific heat. And the lower the specific heat, the more quickly that the temperature changes. So concrete has a specific heat of, let's say, 1. And then grass has a specific heat of 2, and water has a specific heat of 4, which means it absorbs an enormous amount of energy before changing in temperature. Which is why water is really good at stabilizing air temperatures. Has anyone ever been to California or Florida? What's the weather like there? It's not that hot. Like if you compare it to our weather, in the middle of summer, we're going to be somewhere around 120, where you can't even go outside. But in California, can you go outside? Yeah, it's going to be somewhere around 85. Like, it'll be hot, but it's going to be nowhere near the temperatures we have here. Why is that? What's the ocean doing there? It's absorbing a bunch of that heat. And because the ocean is there to absorb heat, the temperature is just going to be cooler there. That's why so many people live in Florida, so many people live in California. All right, let's move on. So here we have another example of specific heat. So does anybody know how a radiator works in your car? All right, so let's talk about engines real quick, and we're going to talk about some components that are really important. So your engine is a combustion reactor. What is combustion? All right, so water is produced in a combustion reaction, but a combustion reaction is basically flames. So fire, explosions are happening inside your engine. So fuel and air and sparks are in your engine, and it's constantly heating up. So if you turn on your engine without your radiator, it's going to hit 600 degrees really fast, and it's just going to keep going up. If your engine reaches the melting point of metal, what's going to happen to your engine? It's not going to explode. If it reaches the melting point of metal, what's going to happen to the inside of your engine? It's going to melt. Your engine will melt. If your engine melts, it's called seizing. When your engine seizes, you have to replace it. So your engine seizes anytime it doesn't have water in it. So water is used to cool your engine. How does the water work? So your engine has the combustion reaction, which is constantly burning fuel and constantly heating up your engine. And then you have cold water that runs through the engine. What does the cold water do when it hits the hot engine? It absorbs the heat from the engine, cooling down the engine, and now you have really hot water. What does the hot water do? It leaves the engine and then it goes to the radiator. Now the radiator, everybody look at this picture. The radiator is right here in front of the car. So as long as the car is moving, what's hitting your radiator? What's hitting the radiator as long as you're moving? Air, right? And the air outside the car, let's say that's sitting at around 100 degrees. It's a really hot day. The air is 100 degrees. What's the water? What's this water right here that just touched a 600 degree engine? This water is probably going to be somewhere around the 200 or 300 degree mark. What's going to happen when it gets hit by that cold air? It's going to cool down. So this really hot water is going to cool down, and then once it's cool, what's it going to do? It's going to continue the cycle. So you have a water pump in your car. What does the water pump do? It keeps the water flowing. So as long as the water is flowing and the car continues to move forward, the water is cooling, the air is cooling the water is cooling the engine heats up the water, and that cycle just goes on over and over again. Now, one other question, this one is a bonus. Has anyone ever heard the car fan turn on when you park it? So next time your parents park the car, you can just stand in front of it and you'll hear the fans running. Why do the fans run when the car is stationary?
So it won't overheat?
Because that's right. So if there's no air going up here, if you're not moving, then you need this fan, and this fan is right here behind the radiator, and this fan forces air through and continues to cool the water. So that fan doesn't ever come on unless the car is stationary. So once the car is parked, the fan comes on. The fan doesn't need to run if the car is going at 60 miles an hour. The air is just flowing on its own. Does that make sense? All right, so why is water really good at this job? Because water can absorb what? It can absorb a lot of heat without doing what? Without changing in temperature. So it can absorb a lot of heat without changing in temperature. So water has a really high specific heat. All right, let's keep going. So next one is heat of vaporization, which is basically the same thing. So think about when you boil water. What are you doing when you're heating up your water? So first you heat up the water. What do the water molecules do after you heat them up? They move more rapidly, right? They start moving really fast. What happens when the hydrogen bonds finally break? What does the water do when it gets so hot that the hydrogen bonds break? All right, so water begins to evaporate, and now you have water vapor. So that's what hydrogen bonds are doing. Hydrogen bonds are keeping the water together. As soon as the hydrogen bonds are broken, the water is free to flow, and then you have vaporized water, or water vapor. And that really applies to the same thing with specific heat. So I just wanted to go over it real quick. All right, next one. This one is probably the most crucial, is density. So most things, when they solidify, they become more dense. Water is an exception to that rule. So everybody look at my screen real quick. So here we have ice, which means here we have a solid. Here we have liquid water, which means here we have a liquid. Which one do you see more molecules in? Do you see more molecules here in solid, or do you see more molecules in liquid? Liquid has more molecules in a given space, which means liquid water is more dense than ice. So when water freezes, does it go up or does it go down? Are you sure? Okay, so the less dense thing is always the thing that goes up. So if you put oil on water, where does oil go? It goes up because it's less dense. So when ice freezes, where does ice go? It goes up. So think about the fish. So fish are swimming underwater. It gets really cold on the surface. And then the water on the surface freezes. If the water went down, what would happen to the fish? They would die. Okay? So if water didn't freeze and become less dense and flow to the top, so when water freezes at the top, what happens at the bottom? Basically, the water at the bottom is sheltered from the cold that's happening at the top, and the fish can survive under the ice. But if the ice went down, then we would lose the fish, and that's detrimental. So density is a really important one. You don't need to write all this. What you need to write is density is a unique property of water. Just about everything else, when it solidifies, becomes more dense. Water is an exception to that rule. When it solidifies, it becomes less dense, which means solid water or ice will float on top of water. And why does it do that? It starts with an H. Hydrogen bonds, good. So the hydrogen bonds, my chemistry teacher said the hydrogen bonds are the answer to everything. If you don't know the answer is hydrogen bonds. And you're not going to see one of these phase diagrams until college chemistry. But water is an exception. You see how, so the way this line works, so you have one going up and then this one comes back. Most things, their line goes forward like this. And that's why water is an exception. So that line, it looks different for water's phase diagram. All right, let's move on. Our last unique property of water is that water is the universal solvent. So to know what that means, we need the definition for solvent. So let's go ahead and write that down. So a solvent is a liquid that dissolves a particle. So the solvent is the liquid that dissolves a particle. So you can take a look here. We have water with M&Ms in it. So in this solution right here, what is water? Is it the solvent or the solute? It's the solvent. And then the solute is going to be what? The M&Ms. Good. So the solvent is the liquid that dissolves a particle, and the solute is the particle or liquid that gets dissolved in the solvent. So example, salt water. Which one is the solvent? Water, good. Which one is the solute? The salt. So why is water the universal solvent? Water is a solvent that dissolves the most solutes. So if you needed to dissolve something, water is most likely going to be the thing you dissolve it in, because water dissolves most things. Anybody want to guess why? Hydrogen bonds, good.
What do you mean by liquid that gets dissolved?
So sometimes you dissolve liquids into other liquids. Like if I were to take hydrochloric acid and put it in water, the hydrochloric acid is dissolving in the water. Another example would be salt. So salt is going to be solid, and when you put it in water, it's going to dissolve or ionize, which we'll discuss very soon. All right, let's keep moving. Thank you, sir. All right, this is for you. Es tuyo. Come grab it. All right. All right, let's move on. Okay, so next thing I want you guys to write down is that like dissolves like. So on your page, like dissolves like. What does that mean? It means polar things dissolve what? Polar things, good. So polar dissolves polar, and non-polar dissolves what? Non-polar, good. So why does this bear look so scared? We're gonna discuss next time about ionic compounds. We don't really need to do that today, but we'll discuss that next time I see you guys. Let's go ahead and keep moving. Any questions on like dissolving like? Anybody here bake? So if you wanted to bake something with vanilla in it, what do you put the vanilla in? What do you dissolve vanilla in? Y'all don't know? Do what? Say it again. It is a wet ingredient. So what do you dissolve? What would you dissolve? All right, let's move on. So our next page is going to be about solubility. This is our next teak. We just finished 2 teaks. This is our 3rd teak today. These are really small teaks, so a couple of them are just 1 question each, which is why we run through them as quickly as we do. But next up, we have a new term. This term is solubility. Go ahead and write out this term, solubility. So solubility is how much solute you can dissolve under certain conditions of temperature and pressure. So how much solute you can dissolve under certain conditions of temperature and pressure. Okay, so solubility is how much solute you can dissolve under certain conditions of temperature and pressure. Basically meaning you can dissolve different quantities based on the temperature of your solvent. So let's go ahead and keep moving. So we have 2 more terms I need y'all to write. First one is going to be miscible. So miscible, those are 2 things that will dissolve into each other. Example is going to be alcohol and water. If you mix alcohol and water, they're going to dissolve and they're going to become one new liquid. Then you have examples that are immiscible. Immiscible is going to be things like water and oil. So when you mix water and oil, you get something that looks like this. And if you shake it up, you get beads of oil. However, you let it sit and they're just going to separate again. So miscible is when they can dissolve into each other. Immiscible, they cannot dissolve into each other. All right, so next we're going to talk about factors that affect solubility. So go ahead and write this down, factors that affect solubility. And first we're going to discuss solids, and then after we'll discuss gases, but just know they're different. So you're going to do factors that affect solubility, and we're going to discuss solids first. So here we have some granular sugar, and here we have a sugar cube. So let's say I have some tea, and this tea is 90 degrees Celsius. And I put a sugar cube in it, and then I have another one, also 90 degrees Celsius, and I put the granular sugar in it. Which one is going to dissolve more quickly? All right, hands up for granular. Hands up for sugar cube. All right, correct answer is granular. So this one will dissolve more quickly. Now let's ignore this one for a little bit, and let's talk only about the sugar cube. What are some things that I could do to make the sugar cube dissolve more quickly? All right, so breaking it down is one thing. What's another thing I can do? All right, I think I heard it. What can I do? All right, so I can heat it up. If I heat it up, it's going to dissolve more quickly. What's another thing I can do? So crush it, heat it up. What else? Stir it. Good. Those are the 3. So I didn't even have to teach you these things. You already know them. So the first one, so solids, this is specifically for solids dissolving in liquids. So the first one is going to be surface area. So as we crush it, we're increasing the exposed surface area. So more of the sugar is exposed to water at any given point, which makes it dissolve more quickly. The second one is stirring or agitating. So stirring or shaking. Agitation is the term that you're going to see used, and you just need to know what it means. You're not making it mad, you're shaking it. All right, last one is going to be the temperature of the solvent. So as we increase the temperature of the solvent, you're increasing solubility. You're also making it dissolve more quickly. And then last one is pressure. Has no effect on solids and liquids. So if I increase or decrease the pressure, it won't change how much or how quickly solid will dissolve. So next up we have factors that affect solubility for gases. And what you're going to notice is it's basically the opposite here. So first of all, surface area is not applicable to gases. Why does surface area not matter for gases? Do gases have exposed surface area? All right, hold up. Her first. Yes. All right, so looking over here, so you can see that with gas particles, the entire surface is exposed. And that's true for all of them. Doesn't matter how much air, volume there is. Surface area has no application for gases. So that's something you're going to want to know. So stirring or agitating. If we stir water or agitate the water, like shaking the bottle, what's going to happen to the gas molecules inside of the liquid? So when the gas molecules, all right, I'm going to pause real quick. Hold up. This ties right into shaking a can and then watching the pressure increase. When you shake it, you're gonna get the gas molecules to escape the liquid. So stirring has the opposite effect on gas molecules. So the next one is going to be temperature of the solvent. And this goes back to what we were just talking about. So if we increase the temperature, what happens to the molecules of liquid? Do they move slower or faster? If we heat up a liquid, what happens to the molecules? They move faster. Do they hold gas molecules better or worse? Worse. So increasing temperature does what to solubility? So higher temperature decreases solubility. Agitation decreases solubility. And then when it comes to pressure, pressure increases the rate of solubility for gases. So you can take a look at this example here. So over here we have little pressure, and you can see how many molecules are in the liquid. And then when we increase the pressure, what happens to the number of molecules in the liquid? Does it go up or down? So take a look at these over here, and then take a look at these over here. What happens when we increase pressure? We increase solubility. Good. So higher pressure increases the solubility rate. So this one, which didn't apply to solids, this one, which doesn't apply to solids, does apply to gases. And then this one, which applies to solids, does not apply to gases. What kind of question do you think you're going to see on the test? A highly missed question on the last test was about how gas molecules move. And a bunch of y'all chose that gas molecules have inelastic collisions. Is that true? No. So that's the type of question you're going to see. I'm going to ask you about gases, and I'm going to give you a property for a solid. I'm going to ask you about a solid, give you properties for gases. So you need to be able to identify them. So here they are all side by side. So temperature, increasing temperature increases solubility. Pressure has no effect. Agitation increases. And then surface area increases. So you can see that temperature, agitation, surface area, they all increase solubility. Whereas for gases, they decrease, they cause to escape, so also decrease. Surface area not applicable. Whereas pressure, that's your only increase right there. You don't need to write these. I just wanted to include them side by side. This video will be up if you missed any of this stuff. All right, so we need to move on. So next up, we're going to talk about solubility curves. So I want you to draw this curve right here. Make sure you put temperature at the bottom. Make sure you put solubility on the side, and then we'll discuss in a minute. All right, so we got two more terms I want y'all to write down. So the first one is going to be unsaturated solution. An unsaturated solution is just a solution that can hold more solutes. Our next term is going to be saturated solution. And this is a solution that's holding the maximum amount of solute at that particular temperature. So who's made Kool-Aid before? Hands up if you've ever made Kool-Aid. Okay, so y'all know how it is. So first thing we do, we take our pitcher, we fill it with water, we put in our little thing of Kool-Aid, and then we start adding the sugar. So you add 1 cup of sugar, and it completely dissolves. You add another cup of sugar, and only half of it dissolves. What happens to the other half that doesn't dissolve? Where does it go if it doesn't dissolve? It falls to the bottom. If you add another cup, what's going to happen? Is it going to dissolve? Where's it going to go? It's going to fall to the bottom. If you taste it and then you add another cup, is the flavor going to change? No. Any additional sugar after it's reached its saturation point is just going to fall to the bottom and it's not going to affect the taste. So let's go ahead and take a look at these examples right here. So next class, this is where we're going to start. I want to come back to this, but I do want to finish up here. Bless you. All right, so take a look at my screen. So at 40 degrees, how much can I dissolve of KNO3? Do y'all see the number for this? All right, 35 grams. So if I dissolve 35 grams, it's going to be saturated. What if I put in 70 grams? How much is going to dissolve in the water? How much is going to dissolve in the water? 35 grams. How much is just going to fall to the bottom? How much is just going to fall to the bottom? If you put in 70 grams, 35 dissolve, how much doesn't dissolve? $35 grams, good. Come on, y'all, lock in. So, all right, I'm gonna have to stop. All right, so let's say we have we put in 70 grams. We just made a saturated solution where we have 35 grams sitting at the bottom. What if I put in 20 grams? Did I make a saturated solution? What did I make? Unsaturated. So under the line, let's all write this down. Anything under the line is going to be an unsaturated solution. Unsaturated solution anywhere below the line. In our last example, we talked about if we put 70 grams, 35 grams will dissolve, and then 35 are going to fall to the bottom. So if I put in 70 grams, what kind of solution did I make? I made a saturated solution. So anything on the line or above is going to be a saturated solution. Below the line is going to be unsaturated. On the line is going to be saturated. Now, our final example is called a supersaturated solution. A supersaturated solution is a solution that holds more than the maximum amount by being heated and then cooled.